Alright, you guys, so let's go ahead and look a little bit of theory. So we've done a lot of practice, we've done a lot of division, whether it was long division or by synthetically doing it. But let's hit some theory, and then after this theory we'll be ready to actually start finding our zeros. So here's the theory. What we do is we have a polynomial, I'll call it f of x, and we're going to divide it by another polynomial, let's call that g of x. So f of x divided by g of x. The answer that we write will be written in the following way. Q of x plus r of x over g of x. And in this case, the f of x is called the dividend. That's basically your numerator when you start. G of x is the divisor. That's the item that we're dividing by. Q of x is the quotient that we get after we do the division. R of x is your remainder, and it will always be a degree less than the divisor. So if you kind of saw that in action quite a bit. Let me go back to one of our previous examples. So you'll notice that we started with a degree 2 divided by a degree 1, and the remainder, right, has a degree less than the divisor. Same thing here, right? Our divisor is degree 1 and our remainder is less than that. And of course that happened on several different occasions, right? In this last one where we had basically my remainder is a degree less than my divisor. Degree less than my divisor, degree less than my divisor. As a matter of fact, if we were dividing by degree 1, then our divisor has to be our remainder has to be a constant. And so we kind of saw this theorem in action. So here's f of x, the dividend. X minus 1 was the divisor. X minus 2 ends up being the quotient. 2 ends up being the remainder. And then we divide it by what we divided by in the first place, which is x minus 1. So here we're just basically, in general, describing what our answer looks like when we divide a polynomial by another polynomial. And we've already done that. We're just kind of summarizing it and formalizing it in some nice functional language. All right. And then here is basically a fact. The fact is that if the remainder is equal to 0, then we can say that g of x is a factor of the polynomial f of x. And here's how we can say that. If we come back up to here, if I was to multiply both sides by g of x, all right, that basically tells me that the polynomial we begin with, f of x, if we distribute here, we get q of x times g of x, plus the g of x's will cancel here, giving us r of x. So our function is basically the quotient times the divisor plus my remainder. But if my remainder is equal to 0, right, this piece is 0, that means that my f of x is basically q of x times g of x. And that's what it meant to factor all along, that we're taking a polynomial and we're breaking it up into a product of two other polynomials. So again, case in point, let's go back to one that we did a little bit earlier where we kind of did this already. Let me try to get this squared away. When I took x cubed plus 27 and divided it by x plus 3, right, we ended up finding that the answer was x squared minus 3x plus 9. There was no remainder when we did that, whether it was long division or synthetically doing it. And what this basically means is that my polynomial x cubed plus 27 is equal to the quotient x squared minus 3x plus 9 times the divisor. And so you'll notice what we did is we started to take this polynomial and we broke it down into its factors, which is really good because if I start seeing factors, I can start to see zeros, right? So we know that if x plus 3 is a 0, then we know that x equals negative 3, right, is going to be a 0 of the polynomial. So you can start to see how the process of division is going to help us actually find zeros. Okay, so this fact now leads us to the remainder theorem. This is actually really wild, is that if we take a polynomial and we divide it by another polynomial to form x minus c, then the remainder is actually equal to f of c. And that is pretty doggone amazing. So let's use that remainder theorem to answer some questions. If I take the polynomial x squared minus 3x plus 4 and I divide it by x minus 2, so we're saying this, right? What's the remainder going to be? Well, according to this theory, because we're dividing of something of the form x minus c, the remainder is going to be f of c. So c in this case is 2. So if I plug a 2 into the function, we get 2 squared minus 3 times 2 plus 4. And this gives us 4 minus 6 plus 4. And it looks like we get a value of 2. So the remainder is actually 2. That's kind of a, there's no link between the fact that C is 2 and the output's 2. Don't read any more into that. It just means the remainder is 2. Of course, to prove that, why don't we do the actual division by synthetically doing this? So if we synthetically do this, drop the 1, 2 times 1 is 2, right? We get a negative 1, 2 times negative 1 is negative 2, and you get 2. So there's your remainder. So the theorem seems to match up with what's being said. Pretty wild stuff. Okay? In the next example, we're dividing by x plus 1. Well, this means x minus a negative 1. So my c is negative 1. So by theory, what's the remainder? Right? Well, it's equal to f of negative 1. So if I plug that in, we get 2 times negative 1 cubed minus negative 1 squared plus 3 times negative 1 minus 5. That is going to result in 2 times negative 1. This will be positive 1. This will be a negative 3 and minus 5. So we get a negative 2 minus 1 minus 3 minus 5. I think when we add all this together, I'm getting negative 11 out of that. Alright, and so there's what the remainder theorem is saying. How about we check it by actually doing the division? So if we did that division synthetically, the negative 1 would go here. I would list my coefficients, drop that down, multiply, multiply, and multiply, and lo and behold, there you go. Right? So there's my quotient, but we're using the remainder theorem. So the remainder, all right, when we divide by something of the form x minus c, the remainder is basically the function value, right? The dividend value at that c. So really, really incredible stuff. And if we would go back to the divisions we did on the previous page, we can actually test that theory. So, oops, not that page. So on this page, how about I do a couple here, right? So we found that if c is negative 3, the remainder is 0. So that means if I plugged negative 3 into this function, negative 3 to the 4th plus 6 times negative 3 cubed plus 8 times negative 3 squared minus 6 times negative 3 minus 9, I'm anticipating a result of 0 out of all this. So negative 3 to the 4th is 81, right? This is 27 times 6, 2 carry the 4, that's negative 102, plus here that's 72, that's an 18 and a minus 9. So adding all this together here, all right, let me make sure I did my, that's 9, that's, oh, that's a positive 18, yeah. I think I did that all right. All right, and 9 times 9, 81. So 81 and 72 and 18, somehow that doesn't come out quite right. What am I doing wrong? Uh-oh. Make sure my remainder was 0. All right, so if we have c is negative 3 to the 4th, 6 times negative 3, maybe I did this wrong. 27 times 6, that's 2, carry the 4, oh, 162. There it is. Now I think it'll come out. And so if we added up 81, 72, and 18, right, 1, 15, 16, that's 171. If I took negative 162 and subtracted 9 from that, that's negative 171. So 171 plus negative 171 gives us an answer of 0. So you can see that that remainder theorem is coming into play. I think I have time for one more. So over up here, our c value is 1. So we know the remainder was 2, but if I plug that in there, right, f of 2 is 1 squared minus 3 times 1 plus 4. That's 1 minus 3 plus 4. That's 5 minus 3, which gives us 2. So there is your remainder theorem in action. Okay? And so now, with all this theory, all right, what we can start to do is finally get to the idea of finding real zeros and tying in a lot of things together and coming up with a game plan on how to find the real zeros of a polynomial. And it's going to involve a lot of synthetic division and pretty much our remainder theorem. But I'll do that in some videos coming soon. See you guys then.